All right, let's get into it. Today, we're staging the ultimate power showdown. On one side, you have the electricity that's in your home right now. And on the other, the heavy-duty power that runs massive factories and data centers. They're not the same, and we're going to find out why. So, have you ever really thought about this? Why can't a giant industrial motor or a rack of internet servers just plug into a regular wall outlet like your TV? It's a great question. And the answer? Well, it's the reason our modern world can even exist. Okay, so here's the fundamental problem. The power grid delivers what we call alternating current, or AC. Think of it as electricity that's constantly changing direction. But all our serious, high-power electronics, they need direct current, or DC, a nice, steady, one-way flow of power. So right off the bat, we've got a conversion job to do. And the hero of this conversion story is this little device called a rectifier. Its whole job is to take that messy back-and-forth AC power and wrangle it into the smooth, predictable DC power that our technology needs to survive. It's basically the bouncer at the door of a DC-only club. So let's start with what we all know, the single-phase power that's wired into our homes. It's perfect for lights and laptops, but let's see what happens when we try to turn it into that clean DC we're looking for. The process starts with the AC coming from your wall. It goes through a simple rectifier, which kind of flips the negative half of the wave up. But what you get out isn't a smooth, flat line. Nope. You get this bumpy, pulsating wave. To smooth that out, you have to add a big, heavy, and pretty expensive component called an inductor. And this right here is the big problem with single-phase power. The power delivery isn't constant. In fact, twice for every single cycle, the power drops all the way to zero. It's an incredibly bumpy ride for any piece of electronics. So just how bumpy is it? Well, if you have 60 hertz power coming out of your wall, which is standard in North America, the ripple on your DC output is double that, 120 hertz. That's a serious vibration that you absolutely have to filter out. And that brings us to this great quote from MIT's David Perrault. You can solve the problem, you just get a big inductor and smooth it out. But here's the thing. In the world of power electronics, big is the last thing you want. It means heavy, it means expensive, and it means inefficient. So if the single-phase method is kind of clunky and brute force, what's the alternative? Well, this is where three-phase power makes its grand entrance. It's the elegant, powerful, and much smoother solution. I love this analogy because it's so perfect. You know, single-phase power is like one person pedaling a bike. You get a push, then a coast. A push, then a coast. But three-phase, that's like having three people pedaling, all timed perfectly so that just as one person's push is ending, the next one is beginning. The result is just this beautifully constant, smooth delivery of power. Okay, so we have this inherently smoother power source. What happens when we put it through the same rectifier process? Well, this is where the real magic happens. Just look at that difference. It's incredible. On the left, with single phase, you have these deep, deep valleys where the power practically disappears. But on the right, with three-phase, before one phase even has a chance to drop off, the next one is already there, kicking in and filling the gap. The valleys are gone. All you're left with are these tiny, manageable little ripples. And here's the number that tells the whole story. With those three phases overlapping, your ripple frequency jumps from 120 hertz all the way up to a whopping 360 hertz. So why is a higher frequency so much better? Well, because it's way, way easier to smooth out. Think about it like sanding a piece of wood. It's a lot faster and easier to sand down tiny, fine-grained bumps than it is to sand down big, deep gouges, right? It's the exact same principle here. All right, it is time for the final verdict. Let's put these two contenders side by side and see who comes out on top for high-power applications. This chart just lays it all out, doesn't it? The ripple frequency is 3 times higher. That massive heavy filter inductor, it becomes, and I'm quoting Professor Perrault again, teensy tiny. The power factor, which is basically a grade for efficiency, gets a really nice bump up from about 0.91 to 0.96. And what's the cost for all these massive improvements? Just 2 extra diodes. It's an incredible bargain. And you can really see that efficiency gain right here. A perfect power factor is 1.0, meaning zero wasted energy. Now, that jump from 0.91 to 0.96 might not sound like a huge number, but Trust me, when you're running a data center 24/7, that little difference adds up to enormous energy and cost savings. And this is the whole shebang right here. This is the crucial point. For the tiny cost of adding just two more simple diodes, you get a filter that is dramatically smaller, lighter, and cheaper. And you get a system that's way more efficient. It's one of the best trade-offs in all of engineering. So, we've gotten into the weeds on the technology, but let's pull back and answer the most important question of all. Why does any of this actually matter? The truth is, three-phase rectification is the unsung hero that's quietly powering almost everything around you. It's in every single car alternator charging your battery. It's the front end for every data center that makes the internet work. It drives the giant motors in factories. It's even critical for cutting-edge fusion energy experiments. If something needs a ton of clean DC power, you can bet three-phase is doing the work. So the takeaway is simple. For all the heavy lifting in our modern world, three-phase power isn't just a slightly better option, it is absolutely essential. The smooth, efficient DC power it creates is what makes everything from global commerce to binge-watching your favorite show possible. It's really amazing when you think about it. This one elegant solution, figured out 100 years ago, became the foundation for so much of our technology. It solved a massive problem. And it makes you wonder, as our demand for energy just keeps going up and up, what's going to be the next big breakthrough in how we convert and use power?